Hello, my name is Katie Bircher, and I'm from the University of Michigan. Today, I'm going to be talking to you about a comparison of linearized, three-phased, unbalanced power flow models. So why do we care about all this? Well, the AC power flow model is non-convex in general, which means that it's often too slow to be used properly in optimizations. But we really want to perform optimizations for things like smart grid technologies and a better understanding of the power network, especially as we add things like more distributed energy resources to our grid. Thus, it's important to use linearized approximations of the power flow model for faster optimization. One example of a linearized approximation for a three-phase power flow model is Lin3 dist flow. Lin3 dist flow neglects the nonlinear loss term and assumes that voltages are balanced throughout the network. There have been some suggested improvements for Lin3 dist flow that use a reference power flow. So a reference power flow is where you take a forecast or a guess about what the power network is going to look like. Then you run power flow for that network and then use information from the reference network to pull into the linearized approximation, and thus you have a more accurate power flow. The improvements suggested are pulling information from the reference power flow about the nonlinear loss term such that you have a constant to represent that, and also about the voltage angle ratio such that that information can be used to better represent the losses on the lines. The way that we are evaluating accuracy of our approximation is by comparing the result from the linearized approximation to results from OpenDSS, which is a known power flow solver. In terms of predictions, we predict that adding information about the nonlinear loss term will be beneficial as long as there is low forecast error, so as long as the reference network is similar to the actual network. And we also predict that getting information about the voltage angle ratio will be beneficial when there is high unbalance, since when there is high unbalance, the assumption that the voltages are balanced throughout the network is very much not true. The first set of results we have here is what happens when the forecast error changes. So this is the difference between the actual power flow and the reference power flow. As you can see, Lin3 dist flow does not change at all depending on forecast error because it is not dependent on the reference power flow. As you can also see, when we add in the nonlinear loss term, the accuracy of the power flow approximation improves greatly for low forecast error as expected. But at high forecast error, also as expected, the accuracy is significantly worse than that of just Lin3 dist flow. And this makes sense because if the reference power flow is incredibly different than the actual power flow, it is not providing useful information. We can also see that the voltage angle does not do much here, mostly because this network was not very unbalanced, and so the assumption that all voltages were balanced basically held true. This second set of results is what happens when we vary the maximum voltage unbalance factor of the network. So as you can see, adding the voltage angle to either just Lin3 dist flow or Lin3 dist flow with the approximated nonlinear loss term, both of those see an improvement at a large unbalance factor. This improvement is not as great when the unbalance factor is smaller, and this is as expected since the assumption that the voltages are balanced is more true at low unbalance than it is at high unbalance. The one thing that we didn't expect was that the voltage angle information does not improve the approximation accuracy that much. We expected it to improve it a lot more. And the reason for this is that we are still making the assumption that the voltage magnitudes are balanced. Having the voltage angle really only improves one element of the voltage unbalance. So in conclusion, what we found is that approximating the nonlinear loss term from the reference power flow will improve the power flow approximation accuracy as long as the forecast error is low. Additionally, adding the voltage angle ratio information improves the power flow accuracy only at very high imbalance, and it doesn't really do much if the imbalance is low. We also saw less improvement than expected because the voltage magnitude is still always assumed to be balanced, regardless of if it actually is or not. Thank you for listening.